Hello viewers, in this video we will see some of the problems which has been came in JEE mains and advanced, okay, which is related to topic thermodynamics. So this is part 1 topic which covers the topics such as first law of thermodynamics and various process. Okay, so now we will see the first problem which has been came in JEE 2019. Okay, we see the first problem. So see the problem. A gas can be taken from A to B via two different processes. Okay, two different pathway. We can say ACB and ADB. So from ACB and ADB. So when path ACB is used, see 60 kilojoules of heat flows into the system. 60 kilojoules of heat flows in the system when it follows the path ACB. So QACB, the value is given as 60 kilojoules and 30 joules of work is done by the system. Okay, so according to first law of thermodynamics, we know that QACB is equal to delta U ACB plus work done ACB. So Q value is given, W is given, so you could easily find the value of your change in internal energy along this path ACB. So this is 100, sorry, this is 60 and delta U ACB plus the W is 30. So automatically delta U in ACB path will be equal to 60 minus 30 will be equal to 30 joules. So change in internal energy along the path ACB we have found as 30 joules. So now if path ADB is used, work done by the system is 10 joules. So work done is they have given 10 joules. We have to find the heat flow into the system in the path ADB. So we have to find this ADB is equal to change in internal energy ADB plus work done along the path ADB. So QADB. So now we see that the initial and final point are same for both the paths. Okay, so it means that the change in internal energy will be also equal along the both paths. Okay, so we can say that delta U of ACB will also be equal to delta U of ADB because they have same initial and final point. So change will be equal. So you could write, we have found it as ACB. So 30, the work done is given as 10 joules. So 10, so totally we have 40 joules. So the heat along the path ADB will be equal to 40 joules is the right answer. Okay. Okay, the second problem. See, in this problem, 200 gram of water is heated from 40 degrees Celsius to 60 degrees Celsius, ignoring the slight expansion of water. So we just slightly ignore the slight expansion of water. The change in its internal energy is close to. Okay, so we know that change in internal energy is so we have already written as NCV delta T. But here they have given the water in terms of mass. Okay, so here they have given 200 grams. So we have to write it as MCV delta T. So it should be in kilogram, but they are given in gram. So convert into kilogram, 210 power minus 3. Specific heat capacity value is also given in this question. So 4184 into the temperature difference. That is nothing but 60 minus 40. The difference means it will be equal for whatever, maybe it is either degree Celsius or Kelvin. The difference will be equal for both the notations. Okay, so this will be 200 into 10 power minus 3 into 4184 into this is 20. So when you do this multiplication, we will be getting 16736 joules. So the internal energy value will be, change in internal value will be 16736 joules. So when you convert it into kilojoules, it will be 16.7 kilojoules. So automatically from the options, option D is the right answer. Okay. The third problem. See, in this problem, a gas is compressed from a volume of 2 meter cube to a volume of 1 meter cube at a constant pressure of 100 Newton per meter square. Okay, we see that some amount of gas is compressed from 2 meter cube to 1 meter cube. Okay, first. Then, after compressing, see that then it is heated at constant volume by supplying 150 joules of energy. So, heat supplied is 150 joules of energy. So what happens to the internal energy of the gas? Okay, see that first the gas is compressed. So as the gas is compressed, we see some work is done on the gas. Okay, so that work can be written as PdV. So here it is, pressure is 100. We see that change in volume is 2 minus 1, which is equal to 100 joules. But this work will be a negative one because it is compressed. So work is done on the system, is negative work. So what happens to, but here they also given heat is supplied at constant volume. Okay, so heat value given as 150 joules. Okay, so according to first law of thermodynamics, you know that Q is equal to delta U plus W. Q is 150, delta U minus of 100. So when you take this minus 100 to the left hand side, it becomes 150 plus 100, which is equal to delta U, which is equal to 250 joules. So here we see that the change in internal energy increases by 250. So this is the right answer. Okay. Okay, the fourth problem. See, in this problem, they are given an insulated container of gas has two chambers separated by an insulating partition. So first we have a insulated container. It has two chambers, 1 and 2, which is separated by an insulated partition. Okay, so one of the chamber has volume. So this chamber contains gas, this chamber also contains gas. So one chamber consists of gas of volume V1 at pressure P1 and temperature T1, and another one will be having at volume V2, pressure T2 and temperature T2. That was given in the question. Okay, see, now see that if the partition is removed without doing any work, we have not done any work, but we are just removing the partition, what happens? What is the question asked? What is the final equilibrium temperature of the gas in the container will be? So we have to find the final equilibrium temperature after the partition is removed. Okay, so now see that the internal energy, as it is a insulated container, we see that there will be no change in internal energy. So we have that total the internal energy, the energy will be the internal energy for this particular partition. See that we have, that is U1 is equal to, can be written as N1C into T1. Okay, for this partition, so let us take this as 1 and this as 2. The internal energy will be N2CV of T2. Okay, this is the internal energy values of both chambers. So now when the partition is removed, we can see that after partition is removed, the internal energies of the individual will be equal to the sum of the total. That will be equal to the total internal energy of the container. Okay, so that you can say that U1 plus U2 could be equal to U. That's it, after the partition is removed. Okay, so what is U1 here? N1 CVT1 plus N2 CVT2 will be equal to, so after partition is removed, number of moles will be the summation of N1 plus N2 into CVT, the common final temperature T. Okay, so now from this, so we see that CV remains common for all the equations. So T could be written as N1 T1 plus N2 T2 divided by N1 plus N2. Okay, this is the expression we have got for the final temperature T. So now from the ideal gas equation, you know that PV is equal to nRT. Okay, so in case of NT, we can replace it by PV by R is equal to NT. Okay, PV by R is equal to NT. So just replace here. So instead of N1 and, sorry, just use this equation. Okay, for N is equal to PV by RT. Okay, so replace all N's by PV by RT. So for N1, P1 V1 by RT1 into T1. Okay, plus here we have P2 V2 by RT2 into T2 by, so here we have P1 V1 by RT1 plus P2 V2 by RT2. Okay, so here we are cancelling the temperatures and we'll be getting P1 V1 by R plus P2 V2 by R whole divided by RT2. Okay, so now I'm writing here. So see, the R value remains common both the equations, so let's remove it. Okay, so P1 V1 plus P2 V2 divided by, so when I take LCM in this equation, see, after removing R, after taking LCM, here T1 T2, so it could be written as, yes, this is T1 T2, here it is P1 V1 T2 plus P2 V2 T1. Okay, so I am now writing about the equations. I'm taking to the, oops, here I am taking, so T could be written as, so by taking this T1, T2 to the numerators, it will be written as T1, T2, P1, V1 plus P2, V2 divided by, so P1, V1, T2 plus P2, V2, T1. So this is the final expression for your T. Okay, so from this, see, option A will be your right answer. Okay. The fifth problem. See, in this problem, they are given three different processes that occurs in ideal monatomic gas as shown in the PV diagram. The parts are labeled as A to B. See, A to B and A to C, A to B, A to C and A to D. The change in internal energies during this process are taken as, so change in internal energy they are given as EAB, EAC, EAD, and the work done in the process as WAB, AC and AD. So what is the correct relation between these parameters? Okay, see, they are given four options. So see that all the process are taken under between the two temperature limits T1 and T2. So which in turn we say that the change in internal energy will also be equal for all the three processes because they are taken between the same temperature limits. So the internal energy will be also equal for all the three processes. So from this option we see that only in option B we see that all the internal energies are same. Okay, so let us see the work done also. The WAB, okay, the WAB, see that here the volume is increased from one value to another, the volume is being increased, so we can say that the work done will be greater than 0. See, in AC the volume remains constant, so here you can see the work done will be equal to 0 because the volume remains constant in the process AC, and in AD we see that the volume is reduced, so we can say that the volume will be less than, or the work done will be less than 0. So from this, option B will be your right answer among the four. Okay. Okay, the sixth problem. See, in this problem, in an adiabatic process, they have given the density of a diatomic gas becomes 32 times its initial value. Okay. So, the final pressure of the gas is found to be n times the initial pressure. So, what will be the value of n? Okay. So, you know that in case of adiabatic process, we know that PV power gamma is equal to constant. Okay. So, what is density? Density is equal to mass by volume. So, from this volume could be written as mass by density. So, replace this value in here. Okay. So, P m by rho whole per gamma is equal to constant. So, in case of adiabatic process, you see that the mass is constant. Okay. So, we can neglect it. So, from this we can say that pressure is directly proportional to the density power gamma as it is a diatomic gas. As a diatomic gas. In case of diatomic gas, you know that the value of gamma is nothing but 7 by 5. So substitute here. So here we can write P final by P initial will be equal to rho final by rho initial to the power gamma. Okay, so here the given the final pressure of the gas is n times the initial pressure. So here it could be written as n times the initial pressure by initial pressure will be equal to, in case of density we see that 32 times is initial value. So 32 of rho I by I whole power. Here the value of gamma is 7 by 5. Okay, so here pi gets cancelled, rho I gets cancelled. So here n is equal to 32 power 7 by 5. This 32 could be written as 2 power 5, 7 by 5. So 5 gets cancelled. So 2 power 7. So when you do the calculation for 2 power 7, it is nothing but accurately it is 128. So the value of n is 128. Okay, so seventh problem. See, in this seventh problem, they have given an engine takes in 5 mole of air at 20 degrees centigrade and 1 atmospheric pressure and compress it adiabatically to 1/10 of the original volume. So here they given the initial volume, let us take it as V1. The final volume is equal to 1 by 10 of your V1. That is 1 by 10 of the initial volume. Assuming the processed gas to be an diatomic ideal gas, okay, made up of rigid molecules. What is the question asked? The change in the internal energy during this process. Okay, we have to find the change in internal energy. So here it is given by NCV delta T. Okay, so you know NCV delta T. So you know the initial temperature. If final temperature is being found, you can easily find the change in internal energy. Okay, so as it is an adiabatic process, Now, what is the relationship between temperature and volume? We know that Tv power gamma minus 1 is equal to constant. We see that T1 V1 gamma minus 1 is equal to T2 V2 gamma minus 1. Okay, so from this T2 by T1 could be written as V1 by V2 whole power gamma minus 1. Okay, so T2 by T1 will be equal to, so you know that V2 is 1 by 10 of V1. So when you substitute here, it will be only 10. Okay, because instead of V2, you will be substituting V1 by 10. 10 will go upwards. So 10 V1 will get cancelled. So remaining will be nothing, only 10 power gamma minus 1. So what is the gamma in your diatomic? It is 7 by 5. You know that gamma is equal to 7 by 5. So T2 by T1 is equal to 10 power 7 by 5 minus 1, which is nothing but 2 by 5. Nothing but 2 by 5. Okay. So then T2 will be equal to T1 into 10 power 2 by 5. So T2 is equal to, T1 is 20 degrees Celsius, converted into Kelvin, it is 293 Kelvin. So 293 10 power 2 by 5. So when you do this calculation, you will be getting approximately 732.5 Kelvin. So we'll be getting the value of T2 as 732.5 Kelvin approximately. So now the change in internal energy, delta U is equal to, so you know that the number of moles is given as 5. So for diatomic molecules, CV value is 5 by 2 of R. It is 5 by 2 into R value is 8.134. So I substitute the value of R here into change in temperature, that is 732.5 minus of 293. So when you do this calculation, you will be getting approximately 45767 joules. So when you do the calculation, you will be getting this answer. So which is nearer to 45.7 kilojoules, which is equivalent to 46 kilojoules. So the nearest integer is, here it is 46 kilojoules. This is the answer for this problem. Okay. Okay, the 8th problem. See, in this problem, they are given which of the following is an equivalent cyclic process corresponding to the thermodynamic cyclic given in the figure. So this is the given figure, PV diagram. See, they have mentioned that specially 1 to 2 is an adiabatic process. Okay, so from the figure we can see that 2 to 3 is a constant pressure process and 1 to 3, or 3 to 1 is a constant volume process. Okay, so we have to see the equivalent figure. Here the options are represented in volume temperature, VT graphs. So we have to see the equivalent graph. Okay, see option A, we see that. See here 1 to 2 they have represented in a straight line. So it is not at all correct, because adiabatic process, the process will be represented in a curved line always. Okay, so this cannot be right. Okay, see B, okay, 1 to 2 they are given in curved position. See 2 to 3, yeah, 2 to 3 is a constant pressure process. As pressure remains constant, we see that volume and temperature are directly proportional. But here we see that when the volume reduces, we see that there is an increase in temperature. So they are inversely proportional. So this could not be right. See in C, here 1 to 2 is adiabatic process. Okay. See 2 to 3 constant pressure process. Here also when volume decreases, temperature also decreases. Okay. And 1 to 3 is a constant volume process. Okay. So C will be the right answer. We will also see the D. So D, 2 to 3 is constant volume process, constant pressure process, but here it is represented as constant volume. So it could not be the answer. So option C is the right answer for this problem. Okay, the 9th problem. See, in this problem, they are given starting at temperature 300 Kelvin, 1 mole of an ideal diatomic gas is first compressed adiabatically from volume V1 to V2. So first case, V1 to V2. This is the first case here. Okay. So here we see that they are given that V2 is equal to V1 by 16. It is already mentioned. It is then allowed to expand isobarically to volume V2. So next process is, first it is compressed adiabatically from volume V1 to V2. Then it is expanded from V2 to 2V2. See here it is V2 to 2V2 in case of by isobaric process. Here it is adiabatic process. Okay. So by using this process, you know the initial temperature is also 300 Kelvin they are given. So what is the relationship between temperature and volume? We know this is the relation in case of adiabatic process. So T1 V1 gamma minus 1 is equal to T2 V2 gamma minus 1. So T2 by T1 will be equal to V1 by V2 whole power gamma minus 1. Okay, so here we can write T2 by T1 is equal to, so you know the V2 is equal to V1 by 16. So when you substitute for V2, V1 by 16, 16 will go upwards, V1 will get cancelled. So 16. Okay, so here it also, as it is a diatomic, they have given where it is, they given as diatomic. So the value of gamma is 7 by 5. So 7 by 5 minus 1 will be 2 by 5. So T2 will be equal to T1. What is value of T1? 300 Kelvin. It is already given 16 power 2 by 5. So when you do this calculation, you will be getting the value of T2 as 909 Kelvin. Okay. Okay, so after finding T2, now let us come to the next second stage of process. Volume moves from V2 to 2V2. So it is isobaric process. So here you can see that volume is directly proportional to your temperature. So we have V2, T2, 2V2, T3. We don't know the value. Let us keep this volume as V3. Okay, this volume as V3. So directly proportional. So V2 by V3 is equal to T2 by T3. So you know that V2 by V3 is 2V2. 2V2 which is equal to, what is the value of T2? We have got 909 by T3. Okay. So from this when you cross multiply, T3 will be equal to 909 into 2, in which T3 is equal to 18, that is 909 into 2 will be equal to 1818 Kelvin. So here the answer is 1818 Kelvin. Okay, this is the final temperature of the gas achieved. Okay, here the 10th problem. See here, they are given n moles of an ideal gas with constant volume heat capacity. So each have n moles have constant volume heat capacity, undergoes an isobaric expansion by certain volume. Isobaric expansion is constant pressure process. The ratio of the work done in the process to the heat supplied is. So you know that work done in a constant pressure process is P into dV. This could be written as, from an ideal gas equation, PV is equal to nRT, it could be written as nR delta T. Okay. So now what is the equation for Q from first law of thermodynamics? Q is equal to delta U plus W. So in case of delta U, change in internal energy, we can write as N. Here it is CV by N, because here is given N moles of ideal gas with constant volume heat capacity CV. So here it is CV with respect to number of molecules. CV per number of molecules. So N into CV by N into delta T. Okay. So next, plus work done, that is in format of nR delta T itself. So Q is N, so here it will be CV delta T plus nR into delta T. So they are asking the ratio of work done and heat supplied. So they are asking the value of W by Q. So what is W? It is nR delta T by, so it is CV delta T plus again nR delta T. So when you remove all the delta T, the remaining is W by Q is nR by CV plus nR. This is the ratio. So this ratio, here we have option A is the right answer. Okay. So in this 11th problem, they have given 1 mole of an ideal gas passes through a process where pressure and volume obey this relation. So pressure P and V obey this relation. Here P0 and V0 they are constants. Okay. Calculate the change in temperature of the gas if its volume changes from V0 to 2V0. Okay. Volume changes from V0 to 2V0. Okay. So now see, let us take this volume V0 as V1. So for this volume V1 as V0, we will find what is the value of P1. So P1 will be equal to, so here it is P0. So instead of V, we have to substitute this V0. So here you see this V0 V0 will get cancelled. So 1 minus 1 by 2. So from this P1 is equal to P0 by 2. So from this P1 is equal to P0 by 2. So similarly for V2 is equal to 2V0. Okay, so we'll do here. So for V2 is equal to 2V0, substitute the value of 2V0 in this equation. So for this P2 will be equal to. So for value of V2 as 2V0, we will calculate the value of P2. So P2 will be equal to P0 1 minus 1 by 2 V0 by 2V0 the whole square. So this will be equal to P0 1 minus 1 by 2. So V0 and V0 will be cancelled. So it is 1 by 4. So here it is P0. So 1 minus 1 by 8. So this will be equal to 7 P0 by 8. So here this P2 is equal to 7 P naught by 8. So we have found the value of P1 as P naught by 2, P2 as 7 P naught by 8. Okay. So let us write it in the corner. So we have got P2 is 7 P naught by 8. Okay, so now we have to find the change in temperature. So you know that change in temperature is delta T, which is T2 minus T1. Okay, so you know that from ideal gas equation, PV is equal to nRT, in which T is equal to PV by nR. So PV by nR. So replace it with respect to the numbers. So it is equal to, for T2 write it as P2 V2 by nR, in P1 write it as P1 V1 by nR. Let us take the nR as common. So here it is P2 V2 minus P1 V1. Okay. So 1 by nR. So replace the values with respect to P0 and V0. So here it is 7 P0 by 8. What is V2 here? It is 2 V0. So P1 it is P0 by 2. Here it is V0. So V1 is V0. So 1 by nR. So when you cancel it, it becomes 4. So when you take 4 as LCM, 7 P0 minus of, here it is 2 P0 V0. So here delta T will be equal to 1 by nR. 7 minus 2 will be 5 P0 V0 by 4. Okay, so 5 P0 V0 by nR. So here they are given the number of moles as 1. Okay, so this equation could be written as delta T is equal to 5 by 4 P0 V0 by R. So this is the final equation. 5 by 4 P0 V0. So option B is the right answer. Okay. Here see the 12th problem. So in this problem they are given a thermally insulated vessel contains 150 gram of water. So we have a container which has 150 gram of water in it, okay, at 0 degrees Celsius. So then the air from the vessel is pumped out. See, it is a thermally insulated vessel, and see when the air is pumped out from the vessel adiabatically. So what happens? Certain fraction of water is converted into ice, and the remaining portion is evaporated at 0 degrees. The remaining portion by itself it is evaporated at 0 degrees Celsius. So they are asking what is the mass of the evaporated water will be. Okay, so they are given all the things: latent heat of evaporation of water, latent heat of fusion of water, all are given. So let us take X mass converted into ice. Let's take X mass is converted into ice. So from this it means that 150 minus X will be converted into, it is evaporated. It is evaporated. 150 minus X is evaporated. Okay. So now here see that some amount of heat is lost for the water to be converted into ice. So here some amount of heat is gained to get evaporated at 0 degrees Celsius. So here according to principle of calorimetry, here they says that the amount of heat lost will be equal to the amount of heat gained. So some fraction of heat is taken by the water to convert into ice. Here some fraction is of some fraction of water takes some heat to get evaporated at 0 degrees Celsius. So what is the heat lost to convert it into ice? It is mass into latent heat of fusion. So what is the mass here for converting into ice? It is X. So X into latent heat of fusion of water is 3.36 into 10 power 5. So this is the heat lost to convert it into ice. So here heat gain. So here it is 150 minus X into latent heat of vaporization of water. Here it is 2.10 into 10 power 6. So here we see this 10 power 5 and from the 6, 5 could be cancelled. So now what is the remaining? So multiply this 3.36 into X. So 3.36X will be equal to, so here it will be 2.10 into 10, only 10, because 10 power 5, here 10 power 5 taken means remaining only 10 is available. So 10 into 2.10, here it is 21. So multiply 21 into 150, here we will be getting it as 3150 minus 21, X. So take this 21 to this side, here it will be 21 plus 3.36, that is nothing but 24.36 is equal to 3150. So when you do this calculation, X will be equal to 3150 by, which is equal to 130 gram. Approximately you will be getting 130 gram for this particular answer. Okay. So we want only mass of water evaporated. So that is something but 150 minus x. So 150 minus 130 will be 20 grams. So option B is the right answer. See here we are also having 130 also. So you should not get confused. See, the correct answer is 20 grams is the right answer. Okay, see the 13th problem. So in this problem they given an ideal monatomic gas is confined in a cylinder. So you have a cylinder here. So we have some amount of gas here. Okay. So which is controlled by a spring loaded piston of cross section. So see that here we have a piston. This is the piston which is connected to a spring. Okay. So here the cross section of the piston here it is given as 8.0 to 10 power minus 3 meter square. Okay. Initially the gas is at 300 Kelvin. So initial temperature of the gas they given it as initial, that is 300 Kelvin they given, and occupies a volume of, see the initial volume is also given 2.4 10 power minus 3. So the initial volume is also given meter cube. Okay, and the spring is in relaxed state. So normally it is in the relaxed state. Okay, so now what happens, the next, the gas is being heated by a small heater. So by this heater the gas is being heated. So what happens, the gas after something expands so that the piston moves slowly by 0.1 meter. And okay, now the force constant, that is the spring constant of the spring, they are given as 8000 Newton meter, and the atmospheric pressure they are given it as, though, that is the initial pressure will be 1 into 10 power 5 Newton per meter square. Okay, so the cylinder and piston are thermally insulated. The piston and the spring are massless, and there is no friction between the piston and the cylinder. No friction between the piston and the cylinder. Okay, what is the final temperature of the gas will be? So as the gas is being heated, you know that the temperature increases. So what is the final temperature of the gas? So we have to find the final temperature. Okay. So before finding final temperature, we will find the values of your pressure and volume. Okay. So see that the initial pressure is atmospheric pressure. So what could be the final pressure? So the final pressure value will be in addition to atmospheric pressure plus. So as the gas expands, you see that the piston moves by 0.1 meter. So that's the total force of the piston is supported by the spring, by the spring. Okay, so the total force here will be nothing but the spring force, that is we call it as K into X, spring constant into distance moved by the piston. Okay, this is the force, because you know the pressure is nothing but force by area. So this is the force by area of the piston. This is the final pressure in addition to the atmospheric pressure. So now we will find the value. You know that it is 1 into 10 power 5 plus what is the value of K? It is 8000. X is 0.1 divided by what is the area they given? The area they are given it as 8 into 10 power minus 3. So 8 into 10 power minus 3. So when you do the calculation, 1 into 10 power 5 plus here also you will be getting it as 8 and 8 will cancel. Here also you will be getting it as 1 into 10 power 5. So here 2 into 10 power 5 Newton per meter square. This is the value of your final pressure. This is the value of your final pressure. Similarly, you will be finding the value of your final volume. So the initial volume is 2.4 10 power minus 3. So see, initial volume. So now the final volume will be equal to this initial volume plus, so as the gas expanded, the piston is moved, there will be some additional volume also. That is volume, you know that that is area into displacement, or area into the distance, the length. So here it is area of the piston into the distance moved by the piston. Okay, so that nothing but you know that 2.4 into 10 power minus 3 plus area of the piston, you know that it is 8 into 10 power minus 3 into 0.1. So you do the calculation. So 0.1 into 8 will be 0.8. So 10 power minus 3 is common. So 2.4 plus 0.8 will be 3.2 into 10 power minus 3 meter cube. This is the final volume. Okay, so please make a note of it. So we have found the final pressure and the final volume. So okay, fine. So after finding these values, you know from the PV ideal gas equation, you know that PF VF by TF will be equal to Pi Vi by Ti. Okay, this is the equation. Okay, so when you substitute, so here, so rub it off So here if we want to find the TF will be equal to PF VF TI divided by PI into VI. So when you do this calculation, 2 into 10 power 5 into what is the final volume I've got? 3.2 into minus 3 into Ti, that is 300 Kelvin, divided by 1 into 10 power 5 into what is the initial volume? 8 into 10 power minus 3. Okay, so here when you do the calculation, whether Ti is 300 Kelvin, 3 into 10 power minus 3. Okay, fine. PF, okay, PI, whether correct. TF is equal to PF into DI. PI into V. So this is my pressure, and sorry, here the initial volume. Sorry, initial volume written as 2.4 into 10 power minus 3. So 10 power minus 3, 10 power minus 3 get cancelled. So from 4 it is 8, and from 4 it is, or it is 3. Or from 8 it is 8 it is 4, it is 3. Okay, so 3, sorry, here this is 2 is remaining. Okay, so 3 and this is 100, so here we're getting it as 800 Kelvin. So the final value we're getting it as 800 Kelvin. So option B is the right answer. Problem. See, in this problem they are given 4 diagrams. So the question they are given that we have 2 isobaric process, 1 isochoric process and 1 isothermal process. So they given collectively the 2, 1 and 1. Okay, we have to find which graph connects the all these processes. Okay, we should have a 2 isobaric process, we should have 1 isothermal and 1 isochoric. Okay, see, let's see what is which is the correct connection. Okay, so we'll come from the A option. See, here we have 2 isobaric process. Okay, one condition satisfied. 1 isochoric, yeah, it is also satisfied. Whether we have to see this curve is isothermal or not. So isothermal means we need that we know the temperature is constant in which pressure is inversely proportional to volume. Pressure is inversely proportional to volume. So here we see that it is directly proportional. See, volume is increased, pressure is also increased. So this could not be the right option. Okay, second graph. Here we see that we have 2 constant volume process, A, B and C, D. So it is also not right. So we have only 1 isochoric process. This is also not right. Okay. The C option, see that here we have 2 constant pressure processes BC and AD and 1 constant volume process AB, and see that CD is isothermal process because as the volume increases, pressure is reduced. Okay, so it is inversely proportional. So option C is the right answer. We will check it for D also. So in D also we have 2 isochoric process. So this will be also not a right answer for it. Okay, so option C is the right answer. Okay, so see, in this 15th problem, they given n moles of an ideal gas undergoes a process A to B. So A to B, okay, as shown in the figure, maximum temperature of the gas during the processes. Okay, so here the limits is given 2 P0 and P0, V0 and 2 V0. Okay, so now we are going to start the problem with the slope intercept form. See, you know that you learned in the mathematics y is equal to mx plus c. This is the slope, we call it a slope equation, y is equal to ms plus c. So in this problem you see that y is nothing but a p. So p is equal to m is nothing but a slope. Okay, see that the pressure reduces and volume increases in this part. So we can write it as this is minus p naught by v naught into x is nothing but v plus c is nothing but the y intercept. So when you extend this line, you'll be getting the y intercept. So here it is p naught, 2 v naught. So next value will be, sure, it is 3 p naught. So okay, so the y intercept value will be nothing but it is 3 p naught. So this is the equation we have got. Okay, so when you cross multiply, we see that p v naught is equal to minus p naught v plus 3 p naught v naught. Okay, so now from ideal gas equation you know that PV is equal to nRT. So you know that P will be equal to nRT by V. Okay, so now instead of this P, replace by this equation. So here it is nRT by V into V naught, which is equal to minus P naught V plus 3 P naught V naught. Okay. Okay, so now let us use this path now. Okay, so nRT, now take V to the left right hand side. Now we can write it as nRT V naught. Okay, so will be equal to minus P naught V square plus 3 P naught V naught into V. Okay, so now take this term to the next left hand side, nRT V naught plus V square, which is equal to 3 P naught V naught into V. Okay, now keep this equation as 1. Let us now keep this equation as 1. So from this equation we see that temperature is a function of volume. Okay, so we have only the terms T and V. Other terms are P naught, V naught are constant terms. Okay, so we see that T and V. So T here, T is a function of, or we can tell it as it is a function of volume. Okay, so now if you do this differentiation, dt by dv is equal to 0. So from this we could easily find the value of your maximum temperature. Okay, so how we are going to find? So now I'm going to differentiate. See, I'm going to differentiate with respect to v, this above equation, the 1. Okay, differentiate with respect to 1, this equation. So now you differentiate it, you'll be getting nr dt by dv into v naught plus, here it will be getting it as 2 p naught v, because v square means 2 p naught v. Here it is equal to 3 p naught v naught. That's all. Okay, so from this dt by dv, here it is nr v naught. Take this term to the right hand side. So 3 p naught v naught minus 2 p naught into v. So from this we can write a dt by dv is equal to pi nr into v naught. So by equating this term to 0, that is dt by dv is equal to 0, which implies 3 p naught v naught minus 2 pi equal to 0. So this term, when it goes to the right hand side, becomes 0. So now 3 p naught v naught will be equal to, so the term will be 2 p naught v. Because I've taken this term to right hand side, now remaining will be 3 p naught v naught minus 2 p naught v. And now we've taken this to the right hand side. Okay, I've written directly. So from this v could be, so what is the value of v? So v will be equal to 3 p naught v naught by 2 p naught. Okay, so from this p naught will be gets cancelled. This will be equal to 3 v naught by 2. So we have got the value of v as, we have got the value of v as 3 v naught by 2. Okay, just make a note of it. Okay. Okay, fine. So after finding the value of v, substitute this value in this equation number, in the first equation. So when you substitute, so we have got 3 as 3 v naught by 2. So now I'm going to rub this. So you know that v is equal to 3 v naught by 2. Okay, so now here when you substitute this, you know that the t will become t max. So nr t max v naught plus, here it is p naught. For v, we are substituting 3 v naught by 2 the whole square, which is equal to 3 p naught v naught. Instead of v, 3 into v naught by 2. Okay, so here nr v naught will be equal to, or plus, here 3 square 9, so here it is 9 p naught v naught square by 2 square, it is 4. So 9 by 4 p naught v naught square. Here it will be 9 p naught v naught square by 2. Okay, so nr t max into v naught will be equal to, take this term to the right hand side. So 9 square by 2 minus 9 by 4 P naught square. So here when you do this calculation, you'll be getting 9 by 4 P naught V naught square. Okay, so this is P naught. So when you take this term to there, so T max will be equal to 9 by 4 P naught V naught square by, so NR V naught. So one V naught will get cancelled. So here the final term is 9 by 4 P naught V naught by NR. So finally I'm writing here, see, T max will be equal to, see from here, 9 by 4 P naught V naught by NR. So T max is equal to T max is equal to 9 by 4 P naught V naught by NR. So from this option, D is the right answer. Okay, so 16th problem asked in JEE Advanced 2016. So in this problem, see that they are given the statement, a gas is enclosed in a cylinder with a movable frictionless piston. Its initial thermodynamic state at pressure Pi and volume they have given changes to a final state. Okay, at pressure and volume. So given the initial initial volume, initial pressure and initial volume, and they have also given the final pressure and the final volume in an adiabatic quasi-static process. So this state is reached by an adiabatic quasi-static process such that they are given the relation also P cube V power 5 is equal to constant. Okay, so we are considering, see, from Pi to Pf has been taken through this adiabatic process. Okay, full stop. Now see that, consider another thermodynamic process. Okay, that brings the system from the same initial state to the final state, because see that the same initial and the same final is being reached by two steps of process. Okay, so for in the previous, initial and final is reached through adiabatic process, but now they are saying that the same final and the same initial state is being reached by two-step process. One is an isobaric expansion and another one is an isochoric process. Okay, see that here this is the diagram which represents this. So initially this is the process, initial and final. So initially we have come to this point, to the initial to final through adiabatic process. Now they says that this initial and final is reached by two-step process, by a constant pressure and a constant volume. So this is the statement. So this is the process they have given in the statement. Okay, so the same initial Pi and Vf. Okay, fine. Okay, so what is the amount of heat supplied? I was asking the amount of heat supplied to the system in the two-step process. Approximately we are going to find the value. Okay, so first I to F is taken through adiabatic process. So here we know that they are given the relation P cube V power 5 is equal to constant. Okay, so now divide this by 3, the powers. So here it will become P, here it will become P5 by 3, which is equal to C for 1 by 3. So C 1 by 3, that is also a constant. Let us take it as K. So from this here, we can say that lambda value is 5 by 3, because you know that P power gamma is equal to constant. Okay, so from this we can see that the value of gamma is 5 by 3. Okay, so now the work done in an adiabatic processes. So work done in an adiabatic process, you know that it is P final V final minus P initial V initial divided by 1 minus gamma. So what is the value of final pressure? They are given 1 by 32 into 10 power 5 into what is the final volume? It is 8 into 10 power minus 3. Okay, so 10 power minus 3 minus of the initial value. This is 10 power 5 and the initial volume it is 10 power minus 3. So this divide by 1 minus 5 by 3. Okay, so when you do this calculation, you will be getting this value 4. So you will be getting it as 25 minus of 75, sorry, minus of 100. Okay, by this will be minus 2 by 3. Okay, so when you do it, we'll be getting it as 75 into 3 by 2. Okay, that will be equal to 2 to 5 by 2. We'll be getting it as approximately 112.5 joules. So the work done in adiabatic process, we have got 112.5 joules. We got it as 112.5 joules. Okay. So in case of the this is the diagram. Okay. So this is the diagram. So initial and final. So see that for both the process, for adiabatic and the two-step process, the same, we have same initial and final point. So the change in internal energy will be equal for all the both the process. So for this process, in case of adiabatic process, you know that Q is 0. So you know that delta U will be equal to minus of W. So from this, delta U will be equal to minus 112.5 joules. Delta U is equal to minus 112.5 joules. Okay, now let us come to this two-step process. Two-step process means I to this point, then to this point. So let us take it as Q of 1 plus Q of 2, because through constant process and then constant volume. So this will be equal to delta U plus W. Okay, so see delta U, you know the value, there is minus 112.5. Work done. Work done will be taken place only by through this constant pressure process. So P into Vf minus Vi. Okay, so which is equal to minus 112.5 plus, so the initial pressure, that is because only work is done only through constant pressure process. So initial pressure is 10 power 5. The final volume value, that is 8 into 10 power minus 3 minus of initial volume, it is 10 power minus 3. Okay, so when you take 10 power as common, you will be getting as 112.5 plus, so 10 power minus 3, 10 power 5, here it will be 10 square into 7, 8 minus 1 will be nothing but 7. So this is 112.5 plus 700. So here it will be approximately, you will be getting it as 587.5 Kelvin. So which is, when you round off, will be the equation 588 Kelvin. Sorry, 588 joules, that's not Kelvin. Joules, they are finding the heat, 588 joules. So this is the amount of heat supplied in the two-step process, 588 joules. Okay, so option C is the right answer for this problem. Okay, now the 17th problem. See, in this problem they given 1 mole of a monoatomic ideal gas is taken along a two cyclic process. So here we have two cyclic process EFGE, EFGE1, and we have EFHE, cyclic process in the PV diagram. Okay, here they say that the processes involved are purely isochoric, isobaric, isothermal and adiabatic. So we have 4 processes in this cycle. So we will see which curves are the correct representation of the processes. Okay, so now with this representation they have given some match. See, they are given the pathway and also the work done. See, the match, the path list 1 with the magnitude of the work done in list 2. So this is the pathway. So through this pathway, this is the match of the work done. So we have to match correctly what is the work done of the respective pathways. Okay, see here. So from this we have two curve paths. So you know that the curved paths, when compared to isothermal, adiabatic will be more steeper. Okay, so this will be isothermal and this will be adiabatic, because this is more steeper than this. So that will be isothermal, this is adiabatic. So now this is isochoric as it is constant volume, and this is isobaric as it is constant pressure. So these are the 4 processes involved in this process. Okay, so now let us take FH, adiabatic process. FH, adiabatic process. Okay, so you know that adiabatic process PV per gamma is equal to constant. Okay, so here we have the gamma value as it is monoatomic, it is 5 by 3. Okay, so see here, so here you know that P1 V1 gamma is equal to P2 V2 gamma. So here the initial pressure is 32 P naught, so initial volume is V naught power gamma, which is equal to, the final pressure is P naught and this is V2. We can keep it as VH. So that is the final volume here, VH whole power gamma. Okay, so this will be, so this P naught and P naught will get cancelled. So we have 32 V naught power 5 by 3 is equal to VH power 5 by 3. Okay, so now take this V0 to this side. So 32 will be equal to VH by V0 power 5 by 3. So now this could be written as 32 power 3 by 5. So now taking this power to this side will be equal to VH by V0. Okay, so this 32 power 3 by 5, this 32 could be written as 2 power 5 whole power 3 by 5. So 5 and 5 gets cancelled. So the remaining is 2 power 3, which is equal to VH by V0, which implies VH is equal to 8 times of V0. So VH is equal to 8 times of V0. So here we have got this value as 8 V0. This point the value is 8 V0. Now similarly, okay, so now make a note of it. Okay, fine. Similarly, so we have found VH as 8 V0. Now consider the isothermal process, that is FG. Similarly, we consider FG, isothermal process. Isothermal process, we know that PV is equal to constant. So P1 V1 is equal to P2 V2. So here it is 32 P0 and V0 will be, here it is P0 into Pg. So P0 and P0 gets cancelled. So you know that Vg will be equal to 32 times of V0. Okay, so here we have got this value as 32 V0. So we have found all the limits. Okay, so just make a note of it. So after finding these values, we will go to the match. Okay, now the first match, G to E. We have to find the work done through this path G to E. It is a constant pressure process. So work done will be equal to PdV. So P is P0. What is the final initial volume? GE. So G 32 V0, E is V0. So 32 V0 minus V0. So it will be approximate up 31 V0. So work done through GE is 31 P0 V0. So for this pathway, see GE 31. So 4 is the first match. Okay. Now along next path G to H. So G to H also it is a constant pressure process. So here also work done is, so pressure is P0, but the values of V0s are 32 V0 minus 8 V0, which is equal to 32 minus 8 is 24. 24 P0 V0. So G to H it is option 3. Okay. Now, so now I am going to rub it. Now next F into H, F to H, adiabatic process. You know that the work done F to H will be equal to final pressure, final volume minus initial pressure, initial volume by 1 minus gamma. So here the value final pressure, that is what we have, F to H is P0. So P0 into 8 V0 minus of 32 P0 into V0. So this is divided by 1 minus 5 by 3. This is above will be minus 24 P0 V0 divided by 2 by 3. So when 3 goes, that is minus 2 by 3. When 3 goes upwards, it is minus 72 P0 V0 by minus 2, which is nothing but 36 P0 V0. So work done through F to H will give you 36 P0 V0. So option 2 here. So the remaining is nothing but 1, but we will check whether we are getting this answer or not. Okay. So make a note of it. Adiabatic is over. Then finally the isothermal. We have F2G. Okay, we have F2G. So you know that work done in it is nRT ln of Vf by V initial or V2 by V1 like that. So nRT here we have, that is final is 32 V0 by V0. So instead of nRT we could replace it by PV. That could be either P1 V1 or P2 V2. whatever, both are same, whatever we value substitute. So it is 32 P naught into V naught ln of 32 V naught by V naught. So 32 P naught V naught. So this could be ln of 32 because V naught gets cancelled. Ln of 32. So here this ln of 32 could be written as 2 power 5. Okay. So here we having the format as ln of a power b. So this ln of a power b could be written as b ln of a. Okay. So now see that here it is 32 P naught V naught 5 ln of 2. So 32 into 5, that will be nothing but 160 P naught V naught ln of 2. So work done F2G will be 160 P naught V naught. So it is the one is the right. This is the match. Oh, I have never written the code. Okay, sorry. The final codes. See, we have the code. Options. We have options. Here we have P, Q, R, S, and we have P, Q, R, S, and the options are A. Wait. Options are 4, 3, 2, 1, and B is options are 4, 3, 1, 2, and C is the options are 3, 1, 2, 4, and D the options are 1, 3, 2, 4. So when you see that 4, 3, 2, 1, so option A is the right answer. Okay, whether it is visible? Yes. So from this code, this is the code R and S. Okay. So from this we can see option A is the right answer for this problem. Okay. See, in this problem they are given 4 options. In JEE advanced, oh, this is advanced. Okay, so JEE it is advanced. So in JEE advanced there may be questions with more than one options are correct. Okay, so here we see that 1 mole of a monatomic ideal gas undergoes a cyclic process shown in the figure. So which of the statement below is are true? Here we have 4 statements. It may be one or maybe 1 or 2 options may be right. Let us see now. So here they given a graph with respect to temperature and volume. Okay. So first option, process 1 is an isochoric process. So from the graph itself, we can see that 1 is not an isochoric process. Okay, so this is wrong. Process 2, see that gas absorbs heat. Okay, so here there is a second process. Here we see that the volume gets increased. So from this we can say that the work is a positive work. Okay, so when the work is a positive work, here you can see that the gas absorbs heat here. So the value of Q also, because it is a constant temperature process, so that there will be no change in internal energy, only there will be heat will be equal to work done. So when the work is positive, you can say that heat is gas also absorbs heat. So option B is the right answer. So similarly option 4 also, see the process 4 also, because the constant temperature, so there is no change in internal energy, only Q is equal to work done. Okay, so from this process we can say that, see here the volume gets reduced. So okay, the volume gets reduced, so we can say that the Q depends on work done. So work done will be negative work, so the Q also will be releases heat. So B is also right. So process, next option, processes 1 and 3 are not isobaric. They are saying that they are not isobaric. Yes, because in isobaric means we say the pressure is constant. It means that volume is directly proportional to temperature. But see what in the case of 1 and 2, here the volume gets reduced. In this curve we see that the volume gets reduced. Here we can see that the volume gets reduced. Okay, but the temperature is increased. Okay, so for the first one, so they are not directly proportional, they are inversely proportional. In 3 also we see that the volume gets increased, temperature gets reduced. Okay, so they could not be isobaric process. So option D also right. So 3 answers are right and only 1 is wrong for this particular question. Okay. Okay, the 19th problem. See, in this problem, they have given a thermodynamic system is taken from an initial state I to a final state with the internal energy value they given Ui as 100 joules to the final state F along 2 different paths. So from I to F, it has taken through 2 different paths. One is IAF and another one is IBF. Okay, so the notations they have given. The work done by the system along the path AF, IB and BF are WAF is equal to 200 joules, WIB is equal to 50 joules, or WBF is equal to 100 joules respectively. The heat supplied to system along the path IAF, IBF and BF, the notations they are given QIAF, QIB, QBF. If the internal energy of the system in the state B is, so B they are given UB separately 200 joules, QIF is 500 joules. The ratio we have to find QBF by QIB is. You have to find the ratio heat supplied along BF and the heat supplied along IB, the ratio between these two processes. So first we will come from IAF. So you know that QIAF from first law of thermodynamics is nothing but change of internal energy IAF plus work done along IAF. So see that IAF, so from I to A it is a constant volume, so there is no work done, only there is work done along A to F. Okay, so this WIAF could be written as WAF. Okay, so what is the value of WAF? They given 200 joules. So here QIAF their value is given as 500 joules. So this is 500 is equal to delta U IAF plus WAF value they given as 200. So from this delta U IAF which is equal to 300 joules. Now let us come to second process QIBF is equal to delta U IBF plus work done. Here we are writing can be written as IB plus WBF. So I am writing it separately WIB, WBF. So delta U IBF is also equal to delta U IAF because both the initial and final are same for both the process. So here it is nothing but this is 300 and here WIB the value is given as 50, WBF it is given as 100. So total QIBF is equal to 450 joules. So total QIBF value is 450 joules. Okay, so this QIBF could be written as QIB plus QBF, which is equal to 450 joules. Okay, now I'm going to find separately QIB. So QIB is equal to delta U IB plus work done through IB. Delta U IB is nothing but this is UB minus UI plus WIB. So what is UB minus UI? UB no, it is 200, UI it is 100. So 200 minus 100 it is nothing but 100. What is WIB? WIB is 50. So 50 which is equal, so QIB is 150 joules. So now QIB is 150. So from this QBF will be 450 minus 150 which is equal to 300. So from this you know that QIB is 150, QBF is 300. So the ratio QBF by QIB which is nothing but 300 by 150 which is equal to 2. So the ratio is 2. Okay. Okay, so here they given a thermally isolated cylindrical closed vessel. This is a closed vessel of height 8 meters. Is kept vertically. Okay, it is divided into two equal parts. So see that it is divided into two equal parts by a diathermic conductor. Okay, two equal parts means this will be 4, this will be 4, this is 4 and this is 4 meters. Diathermic means it means that it is perfectly thermal conductor, frictionless partition of mass. So this mass is 8.3 kg they given. Thus the partition is held initially at a distance of 4 meters from the top. So they given from the top it is 4 meters. Okay. Each of the two parts the vessel contains. So each of the two parts it contains 0.1 mole. 0.1 mole of the ideal gas at temperature. So initial temperature they given. This is the initial stage. Okay. This is the initial stage as the partition. So both sides the temperature is of 300 Kelvin. So both sides is of 300 Kelvin. Okay. Now what happens? See, the partition is now released. So in this position, the partition is being released. So what happens? Due to gravity. So now see what happens. Due to this gravity, the partition, initially it was here. Due to partition, it is moved to some distance x. So now the partition position is here like this. So it has moved a distance x. Okay. So now this distance totally now it will be 4 plus x, and this distance from the bottom it will be 4 minus x. So 4 plus x, and this will be 4 minus x. Okay, so now see, this will be this total from the top to this end till where the plate has been moved. Let us take it as x. So that will be 4 plus x, and this is 4 minus x. Okay, so now first step. So as the partition is moved down, see that some work is done due to gravity. Because this particle is displaced to this distance x due to the gravity. So some work is done, that is taken as the gravitational work. So which will be equal to change in internal energy, because there is no, it is thermally isolated, so no heat is supplied. So that will be equal to the change in internal energy. So work done due to gravity is nothing but weight of the component into this moved to distance x. Okay, which is equal to change in internal energy. So number of moles into Cv into delta T. Okay, so you know that mgx is equal to the number of moles, total number of moles is 0.2, as it is a, so here they have never mentioned about the type of the gas. So let us assume it as a monatomic gas. Okay, so here Cv value is 3/2 for monatomic gas, because they are given anything, they are not mentioned anything about the type of gas. So let us assume it as a monoatomic gas. So 3.2 into R. So the value of R they given 8.3. So into 8.3 into, so this is the final temperature minus 300. Because the initial temperature is 300 Kelvin. Okay, delta T. Okay, fine. So what is M? So M is also they given it as 8.3 kg. So 8.3, the G they were asked to take it as 10. So 10 into the value of x, which is equal to 0.2 into 3/2 into 8.3, 300. Okay, fine. So see, 8.3 gets cancelled. That's 2, and this is 0.1. Okay, so here it is 10x is equal to 0.1 into 3 TF minus 300. So when the 0.1 is taken to this side, it will become as 100x will be equal to 3 TF minus 900. So 900 is taken to this side. So we'll be hitting 100x plus 900 will be equal to 3 TF. Okay, so from this TF could be written as, when taken 100 as common, 9 plus x by 3. So TF is equal to 100, 9 plus x by 3. So now we have found the expression for the TF in terms of x. So first make a note of it. Okay, fine. So we have found the TF as 100, 9 plus x by 3. Okay. So now we know the ideal gas equation, PV is equal to nRT. Okay, so we have, this is the diagram given, and the above portion, let us take it as 2, that is at the final condition when it has displaced to distance x. So the temperature is the final temperature, so this is 1 and 2. So now what is the value of this 1? P1, now we can write, so as it is moved to distance x, okay, so this diagram could be redrawn as, so this is moved to distance x, okay, from this position. So from the top this is 4 plus x, from the bottom it is 4 minus x. Okay, so P1 into V is equal to NR into TF. So this could be written as P1, volume could be written as area into the distance. So area into 4 plus x, which is equal to NR TF. So from this P1 could be written as NR TF by, P1A could be written as by 4 plus x. So P1A is written as nRTF by 4 plus x. Similarly, you have to do it for P also, 2 also, nRTF from this P2 here, this will be A into 4 minus x, which is equal to nRTF. So from this P2A could be written as nRTF by 4 minus x. So we have found the values of P1A and P2A. Okay, so now see that from force equations, see this plate P1A acts downwards, okay, and the weight of this object acts up downwards. P2A, because this is 1 and this is 2, P2A act upwards. So from this we can write like this. So P1A plus mg is equal to P2A. Okay, so now replace this equation with this equation. Now instead of P1A we can write it as nRTF by 4 plus x plus mg plus P2A could be written as nRTF by 4 minus x. Okay. So now we have to solve this. So from this mg could be written as nRTF by 4 minus x minus of nRTF by 4 plus x. Okay, so from this nRTF is taken as common, so this will be 1 by 4 minus x minus of 1 by 4 plus x. So nRTF, when you solve this equation, it will be 16 minus x square and it will be 2x. So nRTF 2x by 16 minus x square. So now here n is nothing but 0.1 and you know the value of r is 8.314. You know the value of TF, we already found it as 100. 9 plus x by 3 into, we have the final equation 2x by x square. So on the right hand side we have mass m, also you know that 8.3 into g is 10. Okay, so from this 8.3 gets cancelled, so 10 will be equal to 0.1 into 100 2x by 16 minus x square. Okay, so when you do the calculation above, so take the denominator terms to this side. Okay, so 10 will be equal to 0.1 into this will be 10, or 100, this is 10, so here will be 9, this will be 18x plus 2x square. Okay, so if you divide by, when you multiply this, it will be 48 minus 3x square. So take this to this side. 480 minus 30 x square will be equal to, but multiply by 10, 180x plus 20 x square. Okay, so now the equation will be, when you rearrange it, the equation will be 50 x square plus 180x minus 480 is equal to 0. Okay, so when you divide it by 10 on equal sides, 5x square plus 18x minus 48 is equal to 0. This is the equation we have got. Okay, so now we have to find the value of x. So x is nothing but minus b plus or minus square root of b square minus 4ac by 2a. So minus of 18 plus or minus square root of b square is nothing but 3 to 4 minus of 4 into a is nothing but 5 into this is minus 48 by 2 into this is 5. So when you do the calculation, you will be getting the value of x as approximately 1.8. Okay, when you do this calculation, you'll be getting the value of x as 1 point. But we have to find the value of distance of the partition from the top. So you know from the top that is nothing but 4 plus x. So from the top, distance is nothing but 4 plus x, which is equal to 4 plus 1.8, which will be equal to 5.8, which is nearer to 6. Which is nearer to 6. So from this we see that the answer will be 6 meters will be the right answer. Okay, for this problem. Okay. So we have solved 20 problems which is related to JEE mains and advanced. Okay, so kindly make use of it for your practice. Okay.